So now we're going to talk about naive Bayes. So Neil touched on linear discriminant analysis, and this is sort of a similar setup. Just for notation, the probability that y is in a given class given x is the probability of, it's this Bayes rule applied again, the probability of x given y and being in a particular class times the probability of y being in that class divided by the probability of x. So this is just what I said. So the probability of, if we observe a bunch of rows and columns, the probability of x given, or finding that probability in a particular class, given that y is in a particular class, is extremely difficult to calculate without a strong set of assumptions. You have to use conditional distributions, like when you don't, everyone who's taken a math stat class, when you don't assume IID, the complications for likelihood function and whatnot get really complicated. So the naive Bayes simplifies the situation by assuming that all predictors are mutually independent given y. So like I said earlier, I dropped this constant because it's just a constant. It's just a scaling factor. We're all going to end up dividing it by this, or the probability of something being in every class by the same factor. So the ordering of classes is going to end up being the same, so it really doesn't matter. So we can simplify this equation into just being the probability of y being in a particular class times the product of each of the individual classes, or the probability of x given that y is in a particular class. So the naive Bayes classifier assigns the class which has the highest posterior probability. So we maximize over the probability of being in a particular class. One of the advantages of the Bayesian framework is that you can assign prior probabilities, and we actually in this case have to assume the probability for class priors. We have two basic options. We can assume that the probability of our response being in a particular class is just equiprobable, 1 over n. That's probably not realistic in most situations, but it is an option that you can use. Calculation from the training set. So the probability of a particular class is the number of samples in class L divided by the number of the total number of samples. This is the default option in the naive Bayes function in the KLAR package. So if you have no other information about what's going on, this is probably what you want to use. But the third option is to use information based on our prior beliefs that y is in a particular class. Something I read about in this situation is that it gives us an advantage to almost selectively sample for our data set. If I know that, say, I always think of classification in the medicinal setting or the hospital setting. So if I know that someone is going to be sick, or if I know 25 people are sick and 25 people aren't, and I want to classify whether or not a new person is going to get sick, and measuring things about them is extremely expensive, I can selectively have my sample be 25% sick individuals, 25% healthy individuals, and then I can now apply the prior probability of them being in a particular class based on that. So I can incorporate that overall probability in the population into my analysis, but still have more information about a particular class and save money along the way.
Is there any issue with using the same data to estimate your prior probabilities and your probability of x given y?
No, I mean, the primary issue is going to be the independence assumption, and when that's violated, and then you're going to have, or no is probably a very simplistic answer. That's probably depends. But I don't know in which situation it depends. So your independence assumption and the density that you choose for the particular class, at least when I was doing a bunch of different generated a bunch of different types of data and was fitting this classifier, those were the primary two things.
So I was confused about that too. So you're using the training set to get those prior probabilities, and you're fitting on that same training data?
Well, I didn't,
That doesn't seem dirty to you?
It works.
But I mean, to me, a prior is your belief before observing data.
So I guess you can't, maybe prior isn't the appropriate word in this setting then. It's just the probability of it being in a particular class and using the training data that you have. Like, to me, I just put that in there. Maybe I shouldn't have, but to me the prior is this part. That's just things that you use when you have no information.
This
So,
is the naive part.
yeah.
Yeah.
So we have to also make distributional assumptions within each class. So in the case of continuous predictors, the class probabilities are calculated using a normal distribution by default. So because of our independence assumption, now all we have to do is calculate the mean of the particular class and the standard deviation of the particular class. And those things just define our normal distribution. Other choices are the multinomial, the Bernoulli, or there are some non-parametric and semi-supervised methods. I'll touch on it in a bit. But yeah, you read up on it more if you're interested in this stuff. So it's going to be a very simple classification problem here. The iris data set I'm sure everyone has really heard of in the R package. So I'm going to fit the naive Bayes function in the KIR package. Just looking at this data, naive Bayes performs relatively well in separation, where there's good separation. So this is the Setosa genus within iris, and it's relatively well separated, so I expect, like just looking at the data, we expect this to be correctly classified most of the time. The other two, there's overlap there, so if we make errors, it's probably in those. And it turns out that's actually the case. And the naive, or some people call idiot Bayes, classifies Setosa correctly 50% or 50 out of 50, and makes 3 errors in the other 2. So you can plot your distributions. Can you not see that properly, or is it just, yeah? Can you see those 2 curves? No? Yeah, it's just the wrong color, never mind. But there's like 2 curves there, which you can't see. It's totally my fault. It's okay. But you can plot the densities that you have, and there's not separation between versicolor and virginica when you look at the slides again, and there's good separation here in the Setosa. So that's also another reason why it was good at classifying Setosa 100% of the time. So an option you have within the naive Bayes framework and in this function is to use kernel densities for estimating the distribution within a class. So all you really have to do is add that line to your code. And instead of fitting a normal distribution, it'll fit just a non-parametric kernel density. So in this case, this is a naive Bayes on the cancer data set. It classified it correctly 96% of the time. That to me, having such a simple model is pretty cool. And also in this situation, our primary goal is probably to find a tumor which is malignant and classified as malignant, and it does a pretty good job of that. When I use kernel equal true, it only slightly increases the classification rate because there was only one predictor, which was sort of not a normal distribution. Any questions so far? Yeah.
What's the difference between this and the usual RTD, like linear discriminant analysis?
Well,
I think you are also estimating the variance of
I think in QD, I honestly don't know much about those 2, but if I remember correctly, QDA, you also have to make assumptions about the correlation, or you have the option of.
You allow the different classes to have different covariance.
Yeah.
Right. That's sort of like what you are doing.
Yes, absolutely. So, like in this, I'm just doing a prior sensitivity analysis in this situation. Maybe this wasn't the best data set because it's really good at the naive Bayes function works really well here. But you can include prior information, and then as you can see, it'll change. This was just having no priors, and having different priors changes the outcomes of your classification. So there's something that I want to mention in this case. I don't know if Bayesians would roll in their grave, but you can specify, like to me, the context of this problem dictates that I would want malignant tumors to be correctly classified as malignant more often. And that would be much better than having a non-malignant tumor being classified as malignant. So I can skew that probability and have the real the training sample set probabilities were 33% and 66%. And with my prior information, I can say, hey, I think the probability of this is 0.9. It's totally wrong. And this is completely ad hoc in the situation, but I thought doing that was kind of interesting. That you can intentionally, depending on the result that you find more valuable, you can set your prior probabilities. And this is not what you're supposed to do, I know. But I thought, I don't know, to me, like, oh, it's improving my decision making, so that's all I really care about. And that's probably not the right thing to say in the statistics department. So I'm going to fit naive Bayes also on a model or on a data set from research done at Kaiser Permanente. That's a Northern California hospital chain. So go NorCal. So you're from SoCal. Do you guys have one? Oh, okay. All right. So California.
We also have it in like Atlanta, so off the brakes.
So this is a data set courtesy of Dr. David Draper at UCSC, and we used it for a class that I had. So the response here is whether or not a child develops sepsis. We have 66,000 observations. A child developing sepsis is an extremely bad outcome. They either die or go into a permanent coma. So we used two predictors, ANC and I2T, or three predictors. Two of them were ANC and I2T derived from a blood test called complete blood count. And the third predictor is the baby's age in hours at which the blood test results were obtained. So like I said earlier, in this scenario, it is likely our goal to correctly predict a kid who actually gets sepsis as having gotten sepsis. Like correctly, that classification to me in this situation is likely more important. Obviously there are going to be other constraints, but that's probably going to be my primary goal. So this is a graph of the sepsis data set. As you can see, there's no separation. Like it's all over the place. This is just an extremely difficult prediction problem. So, however, the naive Bayes function classifies correctly 98.6% of the time. Using the non-parametric estimation has a slightly higher classification rate, but 98.6 is pretty good for me, and it does a much worse job at correctly classifying whether or not a kid gets sepsis into having gotten sepsis. So even though classification, it classifies correctly almost 99% of the time, we're not really meeting our goal. So in this context, maybe we want to look at other things which could work better, or I'll do a little comparison with logistic regression a bit later. So the pros and cons of naive Bayes. Due to the independence assumption, there is no cursive dimensionality. I mean, I haven't really talked about this, but we can't fit models where our parameters, where p is greater than n, without issues here. Our independence assumption simplifies the math and speeds up the fitting process. We can include prior information to increase accuracy, and we also have the option of not making distributional assumptions about each predictor. So the disadvantage is if our independence assumptions don't hold, this model can perform poorly. The non-parametric approach can overfit data, and in many situations. And our prior information could be wrong, and if that's wrong, then you're going to make much worse predictions overall. So, any questions so far? This is the last slide in this section.